Before we get into graphs of the logarithmic functions, I wanted to just give you a couple of properties of logs first. And the first one, which isn't really going to be important to us at this point, but it's going to be important to us when we get into exponential and logarithmic equations, are what are known as the inverse properties, right? And why would we call them inverse properties? Because they pretty much show the fact that that exponents and logs are inverses of each other, right? They undo each other. So if we had something like the log base b of b to the x, right? So we have exponentiation here, right? B to the x, and then we're taking the log base b of that. What happens is you can look at it like these two things here are just canceling each other out because they're inverse operations, and we just end up with x, right? And the same thing over here. If we have the log base b of x, right? So we're taking the log base b of x, and then we exponentiate using base b, right? Again, these two things are inverses of each other, so they kind of just cancel each other out. So you're just, again, left with x. So again, there's really not much to show here. I mean, these things are going to be useful when we solve equations. So like, for example, if you had something like, I don't know, 4 to the 2x power, right? And then what we did is we took the log base 4 of this, you'd have this first scenario here, right? This kind of resembles that statement above. So what ends up happening is these things are inverses, so they just cancel each other out, and you just end up with 2x, right? And then, like on the other hand, say you had something like the ln of, I don't know, 3x minus 1. So we took that and then we exponentiated that using base e, and we have e to the ln of 3x minus 1. This resembles that statement there. So remember, ln is just log base e. So here we have inverses of each other. They just cancel each other out, and we would end up with 3x minus 1. So you can see how these are going to be useful to us when we solve equations, right? Because they're going to help us isolate either this 3x minus 1 in this case or this 2x in this case, right? So if we have an exponential function, we take the log of both sides. If we have a logarithmic function, we exponentiate on both sides, right? And we just end up with what we started with. So here we have 2x and there we have 3x minus 1. So those are the inverse properties, okay? Now, the other two properties that I wanted to give you actually are just and we saw one of these earlier when we did the table in the last video. The log base b of b always equals 1. And why does that work? Because any base, when you raise it to the first power, just gives you back that base, right? So this is always going to work. So like, what are specific examples of this? Saying the ln of e is 1. Saying the log base 3 of 3 equals 1. Saying the log of 10 equals 1, so on and so forth, right? Those are all specific examples of that property there. And the other property is that the log any base of 1 always equals 0. So again, what are specific examples of this? ln of 1 equals 0. Log base 7 of 1 equals 0. Log of 1 equals 0. And again, where did this come from? This came from the fact that when you raise any base, right, any positive number to the 0 power, you get 1, right? When did you get 1? You got 1 with an exponent of 0. So those are just two additional properties in addition to the inverse properties that you kind of want to remember, right? And then, I mean, when we get into the next section, 9.4, we'll have additional properties of logs, but those are just some some basic ones first. Okay, so now we'll get into graphing these functions and what they look like real quick. All right, so I have log base 2 of x and I have log base 10 of x, and I'm asking you to create tables for them. So, and then graph them on the axes that I give you. So y equals log base 2 of x. If x is 0.25, what you really want to do here is think of 0.25 in a fraction form as 1/4. So what you'd ask yourself, again, remember the thinking bubble, is you'd say 2 to what power will give you 1/4, right? Because I'm really doing log base 2 of 1/4, right? Because x is 1/4. So 2 to what power will give you 1/4? Well, 2 squared would give you 4, but remember it's the reciprocal, so you do a negative 2 power, right? So log base 2 of 1/4 equals negative 2. So for 0.5, think of it as a half. So 2 to what power will give you a half? Well, 2 to the first would give you 2, but this is the reciprocal again, so it's going to be negative 1, right? And now 2 to what power will give you 1? That's going to be 0. That was just our property above. That was one of our additional properties that we gave above. Log base b of 1 always equals 0. And then what is the log base 2 of 4? Well, 2 squared is going to give you 4, so this is 2, because that's the exponent. And then what is log base 2 of 16? Well, it's 2 to the 4th would give you 16, so this is 4, right? So here you have the table for log base 2 of x, and then for log base 10 of x, right, just the log of x, when x is 0.1, think of that as 1/10, right? So 10 to what power will give you 1/10? It's going to be negative 1. And again, the thing to remember is whenever you have a fraction like 1 over something, it's always going to be a negative value, right? Because it's going to be a negative exponent. And then what is the log of 1? Well, again, that's just our property from above. Log of 1 is 0. What is log of 10? 10 to what power will give you 10? That's the first power. And that was our other property from above, which is right here, right? Log base b of b always equals 1. In this case, I had log base 10 of 10 equaled 1. And then here, what is log of 100? Well, 10 to the second power gives you 100. And then what is log of 10,000? Well, 10 to the fourth power will give you 10,000, right? With 10, it's fairly straightforward. You just count how many zeros there are, right? So it's a 1 with 4 zeros, so it's going to be 4. If it was a 1 with 8 zeros, it would be 8, so on and so forth. Okay, so there's your tables, and then of course then you can just graph these. So I'll graph y equals log base 2 of x first. So I need x values that go up to 16 and y values that go from negative 2 to 4. So let's see. Could I go to 16 here? Clearly not if I went by 1s, but I guess I can go by 2s on x. So then this would be 2, 4, 6, 8, 10, 12, 14, and 16. And then I guess I'll go by 1s on y. So that's negative 1, negative 2, negative 3. There's 1, 2, 3, 4, right? And what were my points? My points were 1/4 negative 2, 1/2 negative 1. So 1/4 negative 2 is going to be hard to plot. It's going to be all the way down there. And then 1/2 negative 1 is going to be like right here. And then I had 2, 0, right? I'm sorry, not 2, 0. 1, 0, 4, 2, and 16, 4. So 1, 0 is actually going to be right here. Then 4, 2 is going to be up here. And then 16, 4 is going to be up here. So if you can see what happens here, this thing is actually going way down towards negative infinity. But remember, when I raise 2 to a power, I'm never going to get a negative. value. So this thing is never going to go to the left of 0. What's going to happen is 0 is actually going to be a vertical asymptote here. So this is going way down towards negative infinity, and then it's going to come up steep at first, but then it's actually going to get very, very, very flat, because if that's, I couldn't hold steady there, sorry, right? But the idea of this is, if you just think about this, this thing isn't going to get to 5, right? It's not going to reach 5 until x gets to 32, right? Log base 2 of 32 would be 5. And then it's not going to get to 6 until x is 64, so on and so forth, right? It's not going to get to 7 until x is 128. So it's still going to increase, right? It's going to keep going up and up. There's no horizontal asymptote here, but it's going to go up very, very slowly. All right, so that's log base 2 of x. Log base 10 of x is going to be similar, and clearly I'm not going to be able to graph all these points. I mean, I can't even really graph to 100. I mean, I guess if I go by tens, then that last one is 100. So I guess I could do that. Then that's 20, 40, 60, 80, and 100. But the idea is, since I'm going by tens now, and actually I can go by halves on the y probably, right? 1, 2. Since I'm going by tens, where would point 1 be? Point 1 would basically be almost on the y-axis. I mean, it would be just a hair to the right of the y-axis. So the first point there was actually point 1, negative 1. So point 1, negative 1 would be like basically right here. I mean, it would be pretty much on, almost on the y-axis. And then 1, 0 even would be like right here. And that's even too far to the right probably. And then 10, 1 would be up here. And then 102 would be over here. So this one you can see is even more steep over here. Whoa. It's very, very difficult to draw this accurately, right? And then you can see over here, this thing is even flatter than the other one was, right? Because remember, now this thing isn't going to get to 3 even until x is 1,000. So this thing is going to increase even slower than this one is going to increase. All right, so that's what the graph would look like. And then from the graph, you can kind of see what's going on here, right? The domain of this, and I mean the domain of both of them, right? The domain of both of them here, what happens? This thing is getting really close to 0, but never touching. So the domain of this is going from 0 to infinity, right? 0 with the parenthesis to infinity. And of course, the range then is going to be, this is going all the way down to negative infinity. And how high up is it going to go? Remember, it's going to keep increasing. So it's going to keep going to infinity, just very, 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 very slowly. So the range is actually negative infinity to infinity. It just takes a long time to get up there, right? It takes a long time to increase. So the domain is 0 to infinity, and the range is negative infinity to infinity. And now, of course, you can see here there's also a vertical asymptote at x equals 0, right? And then if you think about what happened, this was the reverse of exponential functions, right? For exponential functions, the domain was negative infinity to infinity. And the range was 0 to infinity. And there was actually not a vertical asymptote, but a horizontal asymptote at y equals 0. right? So they just really switched. And that's the idea of what happens with inverse functions, right? If I graph two functions, like let's say I graphed y equals 10 to the x as my exponential function, and then I'll graph y equals the log of x, right, which is base 10 as my logarithmic function. And then I mean, it's not going to be a nice picture in the standard window, but you should at least be able to get the idea. You see what happens? Let me zoom in on that maybe. See if that works. That's a little bit better picture, right? You see what happens here is you have a point here at 1, 0 on the logarithmic graph, and the point here, 0, 1 on the exponential graph, right? You have the point like 1/10 -1 on the logarithmic graph, and you would have the point -1 1/10 on the exponential graph. So what ends up happening is any point xy that is on the logarithmic graph, there's a corresponding point y comma x on the exponential graph, right? So I'll give you a quick for instance. The point 3, 8 is on the graph of y equals 2 to the x, right? Because when I do 2 to the third, I get 8. So the point 8, 3 is on the graph of the inverse function of that, which would be log base 2 of x, right? Because if I did log base 2 of 8, I'd ask myself 2 to what power will give me 8, and it would be 3, right? So what happens is any point xy that's on the 1 graph, the point y comma x, right, just switch them, is on the graph of the inverse function. So you might want to think about that really, right? Usually the way they might write that in like a textbook is they'd say, well, xy turns into y comma x, right, when you take the inverse function, right? So xy on one function, on the graph of one function, becomes yx on the graph of the inverse function. So again, just think about how that works, and it should make a little bit of sense because it'll work with any inverse functions, not just exponential and logarithmic ones. All right. So our next section will get into more properties of logs. Okay.